This video is for the M2 criterion in Unit 14, which is calculating with the gas laws. The procedure is going to be to look at the question, look at the information you're given and which quantities change. Is it pressure? Does the pressure change? Does the volume change? And so on. Then select the relevant gas law to calculate with. Rearrange that gas law, the equation for it, so that you have the quantity you want to find, put the numbers in, solve the problem. So I'll write down the gas law equations over here, and then we'll do some calculations. Boyle's law says that pressure multiplied by the volume is equal to a constant because they're inversely proportional. So the initial pressure times the initial volume is equal to the final pressure times the final volume. That's the equation we will have. Then volume over temperature. Volume over temperature for Charles' law because they're directly proportional. Or, because we have a division in this one, you can also write it this way up. So wherever you have the directly proportional relationships, you can write them either way up, as long as both volumes are on top, both temperatures on the bottom, both temperatures on top, both volumes on the bottom. So you can use whichever one of those, they both will give you the right answer. The way of choosing which one you want to use is, if you want to calculate the final volume, for example, use this one because volume is on top, so the rearranging is easier and quicker. If you want to find a temperature, initial or final, then use this one because the temperature is on top there. So that's how you go about it. So we've got Boyle's, Charles's, and now the pressure. Similarly, we've got the alternative. By taking the reciprocal of both sides, we would end up with this equation, so you can use either of those equations. And then we have the ideal gas. This is actually a combination of the three above. This is for a fixed mass, in this case, fixed mass of gas. So this one says that PV over T is constant. So there's our initial and final, and you can write that the other way up as well, so let's do that. There's our ideal gas equation. If you don't have a fixed mass of gas, if the amount of gas changes, so the number of moles would change, then we can introduce that in here as well. So this is actually PV equals PV over NT. So there's our number of moles here, N, which takes into account the change of the amount of gas. Okay, and then you could flip that one up as well. I won't do that in this case. I'll do a calculation where it's flipped so you can see it there. Okay, so we'll do some questions. These are the questions from the handout that we gave out. So use those, they're also available on Moodle. So I won't write them down in their entirety, but I'll give you enough information so you get the idea of the question and then how to solve it. So the first one is where we have a container and the volume of the container is reduced. That increases the pressure because we already know that it's inversely proportional. So if you reduce the volume of the container, that will increase the pressure, and we need to find out what the new pressure is if we know what the initial and final volume is and what pressure we started off with. So Initial pressure is P1, which is equal to 200 kilopascals. I'm using kilopascals more. I've introduced kilopascals into these questions because when we're doing the real calculations, we're dealing with industrial applications. So just get used to seeing kilopascals around. That's all. It won't really change the answer significantly, just to see them being used. Initial volume. Is 100 cubic meters, and final volume is 50 cubic meters. And what's the we want to find the final pressure. So we need to use Boyle's law, because in Boyle's law we've got pressure change and a corresponding pressure and volume change. So that's all we're dealing with. There's no temperature change, there's no change in mass, so we've got fixed mass here, constant temperature. If you're not told that a quantity changes, explicitly assume that it is, unless one of them will be indicated as an unknown if you need to find out. If you're given one initial quantity and then you need to find a final. But if nothing is said about the volume, assume that it stays constant. So assume that it is unless you're explicitly told that it's not. Okay, so we need to use this equation, P1 V1 is equal to P2 V2. We want to find P2, this one here. So we need to rearrange the equation, so that's by itself. I do that by dividing both sides of the equation by V2, so the V2 will cancel out here and be divided over here. So we get P1 as V1 over V2. You'll see the way I've written it indicates that I have a pressure multiplied by a ratio of volumes. If you rearrange gas law correctly, you'll always get the quantity you want to find is equal to the same quantity, so I want to find a pressure, so it's equal to another pressure multiplied by a ratio of the other quantity, in this case volume. So P1 is, I've got it up here, 200. Now you see it's 200 kilopascals. If I appreciate the fact that my answer is just going to come out in kilopascals if I don't change it, then I don't need to worry about putting in the prefix equivalent. I can just leave it like this. So I'll have V1 100 over 50. And that comes out as 100 over 50 is 2, so it's 200 times 2, which is 400. So my answer comes out in kilopascals, because that's the unit I had initially and I didn't convert. If I had converted it, it'd be times 1,000, so I'd get 400,000 coming out. Alright, that's the first problem done. That's question A. Let's rub this out and we'll do Charles's law calculation. Okay. Conditions here are that the temperature is increased and the volume of our container is adjusted so that the pressure remains constant. We need to find out what the final volume is. So the mass is constant, or N constant. There's no change in N because the question didn't say anything about it, so the amount of gas stays the same. T is increased, V altered. That means that V did change, and pressure is constant, because we altered the volume so that the pressure would stay the same. So that means this is a Charles's law question, and we have T1 given to us as 17 degrees C. V1 is 150 centimetres cubed, so this is more a small container, whereas previously we were dealing in hundreds of cubic metres, so that's a much larger gas storage. This is not an industrial one really. And then we have T2, it's 37 degrees C. We need to find out what V2 is. Okay, it's always a good idea to write down what quantities you have. It's easy to see which equation to use. We're going to use one of these equations. The way that we choose which one is we want to find V2, so we need to use the equation which has the volume on top. That's this one here. So we're going to use the one on the left. Let's write that down. V1 to V2. And we'll rearrange it. So V2 is equal to V1 times T2 over T1. Now before I start putting my values in, there's an important conversion to do, which is for these two temperatures here. They are given to us in degrees C, but all the gas laws, wherever you see a temperature, that must be in Kelvin, must be on the absolute scale in order for the relationship to work. So we need to do our temperature conversions. To convert from degree C to Kelvin, we need to add 273. So this would be 290. I'll write down the working. 17 plus 273, 290 Kelvin. T2 is equal to 37 plus 273, which is 310. So I've done the temperature conversions. I now need to put my values in to this. So V1 was 150, and T2 is 310, 290. And then we get, if we put the values in, we get 160 centimetres cubed. So that's the second problem solved. In the first case, in the first question, you saw that the pressure, the volume halved and the pressure doubled. So that was a nice, neat thing. You probably, well, quite possibly wouldn't have needed to use the equation to work that out, though you should in all of your working, show all your working. And in this case, you can see there wasn't a nice, neat half or a third or anything like that. So you need to be able to use these methods to solve the problem. Okay, that's second question. I'm just writing up here that the temperature in Kelvin is equal to the temperature in degree C, which is that theta there, plus 273, so just as a reminder for us. Okay, we have another one, and here there's a temperature increase. That leads to a pressure increase. We need to find out what the final temperature is if we are measuring, we're monitoring the pressure. So, T increase. The data is, we have the initial pressure, it's 100 kilopascals. The initial temperature, let's write it as theta 1, just so we know we're writing it in degrees C, 27 degrees C. And then the final pressure, 120 kilopascals. When we find, we want to find so we want to find this final temperature. We want to find the final temperature. It's better to state a final temperature in degrees C because that's more commonly used, and more people can set that into the right context and have an idea of what a temperature in degrees C means, rather than something in Kelvin. So Kelvin is very, very scientific. So we will convert all of our temperatures into degrees C if we're calculating a temperature. And so should you do that. So theta 2 is actually what we want to find. This one we need to turn into Kelvin, so that's 300 Kelvin, and we need to find theta 2 or T2 in order to find this, in order to solve this problem. We need to use this equation here. This is the one with a change in pressure, change in temperature, and temperatures on top, so we want to use that one. So T2 is equal to, if I write out P2, T1, P1, so T2 is equal to T1 times P2 over P1. T1 is 300, P2 is 120. Again, notice both of these are in the same unit, so I don't need to convert. If one of them was in pascals and one was in kilopascals, then I would need to convert, but usually your pressures are not changing enough to change the prefix. So we'll just leave the units. The ratio will sort it out for us. Okay, so that temperature then is 360 Kelvin when you work it out. So we've used the gas law, we've come up with an answer, but we need to do a conversion now back to degrees C. So theta 2 is equal to T2. Now here we're going not from degrees C to Kelvin, we're going from Kelvin to degrees C. So we need to minus 273. So if you do 360 minus 273, then we should get 87 degrees C, and that's the answer that we would state. So you see how you can kind of understand 87 degrees C is very hot, whereas 360 Kelvin maybe not. You could understand what that means. Okay, we have one more problem to do. Now we're on to question D. Okay, here we have a container of gas, and more gas is pumped in. So that means there's a change in N. There's a change in the number of moles of gas. Gas is added. And that leads to a pressure change, temperature change, but not a volume change. The volume is not altered, so the volume is constant. Okay, so which equation do we need to use? We need to use one that has got change in N, change in pressure, change in temperature. And if we use the, well, you'll see over here that only this equation has got PT and N in it. However, it's also got V in it. But if V1 is, if the volume is constant, then V1 equals V2, and that will cancel out the equation. So we'll use that equation, cancel out the V's, and then rearrange it. Now notice I want to find N. I want to find what the change in N is. So N, well, actually you don't know that yet. I haven't stated what the quantities are, so let's write the quantities down. The initial pressure, that's 300 kilopascals. Initial temperature is 17 degrees C. N1. (50,000 moles). Final pressure P2 is 350 kilopascals. Final temperature is 37 degrees C. And we want to find out how many moles of gas were added. So that's what we want to find out. We want to find out how many moles are added. So therefore we need to use this equation. But because what we'll do is calculate N2 and then deduct N1 from it. We want the variant of this equation where N2 is on top. So the equation then, if I flip that, it was both sides of that equation. M1 T1 over P1 V1 is equal to N2 T2 over P2 V2. V1 equals V2. That came from here, so V1 equals V2. So that will cancel out. That makes our equation a bit nicer to work with. So we can rearrange that now. For N2, to make N2 the subject, I need to multiply by P2 to take it over to the other side, and divide by T2. So N2 is equal to N1. Again, you're going to see that it's equal to the number of moles multiplied by a ratio of quantities, except instead of having just one ratio of quantities, there'll be a ratio of temperatures and a ratio of pressures. So this will be N1 T1 over T2 multiplied by P2 and divided by P1. So I've got a ratio of temperatures there, a ratio of pressures. Okay, I can put my values in now. It's 50. Oh no, I can't, because I need to convert these into Kelvin. So T1 is equal to 17 plus 273, that's 290. And this T2 is equal to 310. Now I can put my values in. T1, 290. P2 is 350. Both are in kilopascals, so I don't need to worry about any unit conversions. Divided by T2, which is 310, multiplied by 300. Okay, and when I solve that, I get 54,570 when I round it up. That's not the solution, that's the first part, but I wanted to find out how many moles were added, not how many moles I ended up with. I started off with 50,000 and I finished with 54,570. So if I do N2 minus N1, that'll tell me how many moles were added. So delta N is equal to N2 minus N1. So 4,570 moles of gas were added. So that's my solution. You could round that up further to 2SF if you wanted to, so 4,600 moles were added. And that's the fourth and final example. Hopefully it's been useful to see you going through those, and then you can go back and see any of those examples again in your own time and try working through them. And if you've got any further questions, then just ask me in the lesson. But hopefully that's helpful.